Good day, everyone. This is Engineer Magkuya, and we're going to have our continuation of discussion about vector spaces. For this week, we will be discussing basis and dimension. The objectives for this lecture would be to recognize bases in the vector spaces r raised to n, p sub n, and m of m comma n, and find the dimension of the vector space. Basis for a vector space. A set of vectors S composed of the vectors v1, v2 up to v sub n in a vector space V is a basis for V when the conditions below are true. So it must be a spanning set. S must be a spanning set of V, and the vectors in S are linearly independent. Moreover, if a vector space V has a basis with a finite number of vectors, then V is finite dimensional. Otherwise, V is infinite dimensional. The vector space V equal to the set that contains the zero vector consisting of zero vector alone is finite dimensional. Example, show that the set of example, for the standard basis of R cube, show that the set below is a basis for R cube. S is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. In an earlier example, we showed that S spans R cube. Furthermore, S is linearly independent because the vector equation C1 times 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times 0, 0, 1 is equal to 0, 0, 0. Has the only trivial solution. So you may wish to verify that this would give us C1 equal to 0, C2 equal to 0, and C3 equal to 0. The manual solution for this one would be provided in a file in your Blackboard section. So S is a basis for R cube. So you have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Uniqueness of basis representation. If S equal to v1, v2 up to vn is a basis for the vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in S. Let U be equal to u1, u2, u3 be any vector in R cube. Show that the equation U equal to C1 V1 plus C2 V2 plus C3 V3 has a unique solution for the basis S equal to V1 V2 V3, which is equal to 1 2 3 0 1 2 negative 2 0 1. So to solve this problem, we are going to write this one as a linear combination. You're going to write a given vector in R cube as a linear combination of 1, 2, 3, 0, 1, 2, and negative 2, 0, 1. So you're going to write this down as x equal to C1 U1 plus I think it is C1 V1 plus, wait, so to solve this problem, what we're going to do is to write the vector x as a linear combination C1 V1 plus C2 V2 plus C3 V3. So you have C1 multiplied to the first vector plus C2 multiplied to the second vector plus C3 multiplied to the third vector. So that would be C1 minus 2C3 2C1 plus C2 plus 0C3, 3C1 plus 2C2 plus C3. So this would form your augmented matrix A, and then the unknown vector x equal to U. We can solve this using Gaussian elimination or Gauss-Jordan elimination. So the matrix A is invertible, so you know that the system has a unique solution. C is equal to inverse of A times U. So you can verify this by finding the inverse of A such that C1, C2, C3 is equal to negative U1 plus 4U2 minus 2U3, 2U1 minus 7U2 plus 4U3, and negative U1 plus 2U2 minus U3. For example, if U is equal to 100, this can be represented uniquely as negative V1 plus 2V2 minus V3. Basis for a vector space. Basis and linear dependence. If S is composed of the vectors V1, V2 up to V sub n, this is a basis for a vector space V. Then every set containing more than n vectors in V is linearly dependent. So again, if you have n vectors and the set contains more than n vectors, so if the number of vectors is higher than n, then automatically you can say that they are linearly dependent. You need n vectors to represent, you need at most n vectors to represent linear independence. So if there would be more than n vectors, automatically one of the vector is a linear vector of the other. One vector is a linear combination of the other vector. So that means it is linearly dependent. So these are some of the examples about that. R cube has a basis consisting of 3 vectors. So since this is R cube, we are expecting 3 vectors. First, second, and third vector. So these 3 vectors is sufficient to determine linear independent vectors. But since there are 4, so that means one of this can be written as a multiple or a linear combination of the other vectors. Another one, P3 has a basis containing 4 vectors. So P3, so that means you have A plus BX plus CX squared plus DX cubed. So this is P sub 3, a polynomial of degree 3. How many components does this vector have? A, B, C, and D. So that's 4 components. So that means it needs at most 4 vectors. But for this example, we have 1, 2, 3, 4, 5. So there are 5 vectors. So automatically, this set of vectors are linearly dependent vectors. Number of vectors in a basis. If a vector space V has one basis with n vectors, then every basis for V has n vectors. Again, if a vector space V has one basis with n vectors, then automatically we can say that every basis of V has n vectors. So explain why each statement is true. The set S1 is composed of 3, 2, 1, 7, negative 1, 4 is not a basis for R cube. So if it is R cube, we need 3 vectors. There are only 2 vectors, so meaning we are lacking one more vector to form the spanning, we need one more vector to form the spanning set of R cube. While for the second one, so the set S is not a basis for P3. So P3 means for components. So you have 1, 2, 3, 4, 5. So you have 5 vectors. So this is not linearly independent. So therefore, not a basis. For this one, for it to be a spanning set, you must have 3 vectors. So it's not a basis for R cube. So the standard basis for R cube is S equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Thus, there are 3 vectors in the basis for R cube. So all vectors of the standard basis of R cube has 3 vectors. So if we are referring to any R cubes, there must be 3 vectors in its basis. But since the example has 2 vectors, so it's not a basis. While for this one, a standard basis P sub 3 has 4 vectors. So there are 5 polynomial vectors given. So that is not a basis for P sub 3. The dimension of a vector space. If a vector space V has a basis consisting of n vectors, then the number n is the dimension of V, denoted by the dimension of V equal to n. When V consists of the 0 vector alone, the dimension of V is defined as 0. So the dimension of V is the number of vectors in the basis. So find the dimension of each of the subspaces of R cube. Find the dimension of each subspace of R cube. So for W, we have D, C minus D, and then C. So this is a vector in R cube, where C and D are real numbers. So our representative vector is D, the second component is C minus D, and the third component is C. So we can write this down as D, C minus D, and C. It can be written as DC minus DC, which is equal to 0cc plus D minus D 0. So we can collect the D terms and the C terms. So that would be D negative D 0 and 0cc. So 0cc and D negative D 0. So the two vectors that forms a basis would be 0, 1, 1 and 1, negative 1, 0 for any vector or for any scalars C and D. So we can now say that the subspace, that the dimension of the subspace is 2 because there are 2 vectors which composed of 0, 1, 1 and 1, negative 1, 0. You can show that this set is linearly independent. So S is a basis for W, and W is a two-dimensional subspace of R cube. So it's not necessarily N, it is a subspace. So it is of smaller magnitude. So the dimension of the subspace W can be less than or equal to N. Next. By writing the representative vector, so let's go back to that slide. So you have 2b, b, and 0. So for 2b, b, and 0, you can factor out b. So that would be 2, 1, 0, 2, 1, 0. So you can see that W is spanned by the set S equal to the vector 2, 1, 0, where b is any arbitrary constant. So the dimension of the subspace of that R cube is 1. There's only one vector that can define all the elements of the subspace. Basis test in an n-dimensional space. Let V be a vector space of dimension n. So the dimension is n. So meaning it is considering all the possible vectors. So if S is composed of the vectors v1, v2 up to vn, this set of vectors is a linearly independent set of vectors in V, then S is a basis for V. So if the given set of vectors are independent set of vectors in V, then S is a basis for V. And if S is equal to V1, V2, V3 up to V sub n spans V, then S is also a basis for V. So if there are n vectors and it is linearly independent, then it forms a basis. If there are n vectors and it spans, then it is a basis for V. Show that the set of vectors is a basis for M51. So 5 rows, 1 column. So 1, 2, 3, 4, 5, 1 column. So these are the 5 matrix vectors. So first vector, second vector, third vector, fourth vector, and fifth vector. What we're going to do is to write this down as linear combination and check whether it is a spanning set or if they are linearly independent. Since there are n vectors, since there are 5 vectors for this 5 by 1 matrix vector, so we can either check whether it is a spanning set or linearly independent. So I think it's easier to check linear independence because we are checking whether it is equal to 0. So writing it down, so you have C1 is equal to 0, 2C1 plus C2 is equal to 0, negative C1 plus 3C2 plus 2C3 is equal to 0, 3C1 minus 2C2 minus C3 plus 2C4 is equal to 0, and 4C1 plus 3C2 plus 5C3 minus 3C4 minus 2C5 is equal to 0. We're going to provide the manual solution for this one at the file section of our page. Now, since C1, from this equation, C1 is equal to 0. So if C1 is equal to 0, then automatically we can say that C2 is 0 because C1 is 0. Now, take note that C1 is 0, C2 is 0, so therefore C3 must also be 0. C1 is 0, C2 is 0, C3 is 0, so therefore C4 is also 0. C1, C2, C3, and C4 are 0. So basically, we have C5 is also equal to 0. So it forms a trivial solution. So only trivial solution exists. So it is linearly independent. Thus, it is a basis. So this system has only trivial solution, so S is linear independent. Thus, by that theorem, S is a basis for M5, 1. So that's all for our discussion today. Hope you learned a lot.